Let's see next topic everyone, electric field due to finite line charge. So we have one finite line charge everyone. And let's suppose on this rod we have lambda charge density. All right. And on this rod we have positive charge and charge density is lambda. And we have here one point P. At this P point we want electric field due to this line charge everyone. Correct? Due to this rod we want electric field at the P point. So what we will do it here everyone, first of all we will connect this and this P point, and then we will connect lower end point and this P point. All right, and then we will make or we will draw one perpendicular on this rod. So we will draw here one perpendicular. So this is the perpendicular everyone, and it is making 90 degree on the rod, and this is upper angle theta1 and this is lower angle theta2. So upper end of the rod is making theta1 angle, and this angle we are measuring in clockwise direction. Remember this thing is also, and this angle we are measuring in anti-clockwise direction. So lower angle we are measuring in anti-clockwise direction, and upper angle we are measuring in clockwise direction. So it is positive and this is also positive everyone. So at this P point we have two component of electric field, perpendicular component E perpendicular and we have E parallel. All right, so E perpendicular value is what everyone, it is k lambda by d sine theta1 plus sine theta2. Theta1 is the upper angle, theta2 is the lower angle. D is what here, D is the perpendicular distance between the rod and the P point. So D is the perpendicular distance everyone between the rod and the P point. All right, so this is the perpendicular component and this is the parallel component. We need to remember this both the formula. Here derivation is not required, derivation is very lengthy also, directly we can remember this formula. And if suppose we want net electric field at the P point, then what we can do it everyone, net electric field can be written as under root E perpendicular square plus E parallel square. All right, this thing can be written as, and if you want direction of net electric field at this P point, so what we can do it for the direction, put here one test charge. Okay, and you can do it one more thing here. Let's suppose net electric field in this direction we have, and this angle is theta, we want this angle, so tan theta can be written as what, now we are looking for the direction. Correct, tan theta is equal to what, this angle is theta, so this is perpendicular by base, means E parallel by E perpendicular. All right, so tan theta equal to E parallel by E perpendicular. So if you will look here everyone, and we will put this E parallel and E perpendicular value and we will simplify, then we will get direction. All right, so for the direction we will use this formula, and from this formula we will get net electric field after simplification. So I hope this both things are clear to everyone. Now we will discuss two cases everyone, electric field due to the semi-infinite line charges and electric field due to infinite line charges. So one by one we will discuss. So now we have one semi-infinite line charges. So at one side it is going till infinite everyone, and P point is present at the end of the rod, correct? So here P point is present. All right. And perpendicular distance between the rod and this P point is what it is D. Now, what is the theta 1 and theta 2 angle, everyone? Theta 1 is the upper angle, theta 2 is the lower angle. So theta 1 is what for the semi-infinite one? It is 90 degree. Because end of the rod we don't know. It is going till infinite. So if you want a theta 1, so we need to connect end of the rod with the P point. So when I will connect, so this is going till infinite. Because and we know that. So approx it is 90 degree. So theta 1 is approx 90 degree and theta 2 is what? It is 0 degree, everyone. So what is the value of theta 2? It is 0 degree, correct? So theta 1 is 90 degree, theta 2 is 0 degree. This thing we are getting here. Now the next thing is what here? We will find here E perpendicular and E parallel component. So E perpendicular component formula is what? K lambda by D sin theta 1 plus sin theta 2. Charge density we are assuming here lambda, correct? So first of all I am writing here E perpendicular. So formula of the E perpendicular is what? It is K lambda by D, correct, sin theta 1 plus sin theta 2. So theta 1 is 90 degree, theta 2 is 0 degree, everyone. So E perpendicular equal to K lambda by D sin 90 plus sin 0. And the value of sin 0 is 0, sin 90 is 1. So E perpendicular finally we are getting K lambda by D. This thing we are getting, everyone, K lambda by D. Now the next thing is what? E parallel, everyone. Formula for the E parallel is what? K lambda by D cos theta 2 minus cos theta 1. So now we are finding E parallel K lambda by D cos theta 2. And what is the value of theta 2, everyone? It is 0 minus cos theta 1. And what is the value of cos theta 1? 90 degree. Theta 1 is 90 degree. Cos 90 is 0, cos 0 is 1. So E parallel we have again K lambda by D. So if you will look here, E perpendicular and E parallel, both are K lambda by D, K lambda by D. Alright, now we want direction of net electric field at the P point and we want net magnitude also. So there's both things we want. So let's see it. First of all, we are finding here net magnetic field. So E net can be written as under root E perpendicular square plus E parallel square. Alright, so both are same, everyone. So we have K lambda by D plus K lambda by D. So if you will do the square of this both, so this is 2K lambda by D whole square. So we are getting 2 root 2 K lambda by D. This is the net electric field. Alright, so net electric field we have root 2 K lambda by D. Now we want direction also. So we want direction of net electric field at the P point. So this is E perpendicular. If you look this, everyone, this is E perpendicular and this is E parallel, and this is the direction of net electric field. So let's suppose this angle is theta, everyone. We are looking for this angle theta. All right. So now the next thing is what here? Tan theta equal to E parallel by E perpendicular. and E parallel and E perpendicular both are equal, correct? K lambda by d, K lambda by d, so it is 1. So tan theta equal to, we are getting 1 here. So tan theta equal to 1, so theta equal to how much? It is 45 degree. So 45 degree we will get. This is the direction of net electric field, and net electric field magnitude is root 2 K lambda by d. So I hope this thing is clear to everyone. Now let's see next case everyone, electric field due to the infinite line charge. So right now we have infinite rod everyone. And due to this rod we want electric field at this P point. Correct? At this P point we want. So what we can do it here, first of all we will draw one perpendicular from P to this rod. This thing we will do. Okay, and this perpendicular distance is, let's suppose d here, and it is making 90 degree. So here theta 1 is 90 degree and theta 2 is also 90 degree when rod is infinite. Because if I will connect upper end, so we don't know where we have upper end, so line joining will go till infinite. So here we have 90 degree and this side also we have 90 degree. So theta 1 as well as theta 2 both are 90 degree, correct? Okay. So we are looking for the E perpendicular and E parallel and net electric field and direction of the net electric field. This all things, for this all things we are looking. So first of all I am writing here E perpendicular. So what is the formula of E perpendicular? It is K lambda by D sine theta 1 plus sine theta 2. This is the formula, correct? Theta 1 is 90 degree, theta 2 is 90 degree, and we know that sine 90 is what it is, 1 everyone. So 1 plus 1 is what it is 2. So what we are getting, 2k lambda by d. This is E perpendicular, correct? Now E parallel, what is the form of E parallel? It is k lambda by d cos theta 2 minus cos theta 1, correct? So E parallel we have k lambda by d cos theta 2 minus cos theta 1. Theta 2 is what is 90 degree, cos 90 value is 0 0, so it is 0 everyone. So E parallel finally we are getting 0. So E parallel we have 0, E perpendicular we have 2 lambda by d. Alright. So net electric field at the P point is equal to what? It is equal to E perpendicular. So if I will write net electric field, so it is equal to E perpendicular because E parallel is 0 here. So net electric field is what is 2k lambda by d. And if you will see direction of net electric field, so definitely it should be in this direction. Alright, so this we will get. So I hope this thing is clear to everyone. Let's see this question everyone. A charge q of mass m is placed at a distance r1 from the infinite long uniformly charged wire. What will be the velocity of the charge at a distance r2 from the wire? Take initial velocity of the charge to be 0. So when it is at r1 distance, so velocity is what? It is 0. This thing we need to consider. And we want velocity of this charged particle when it is at r2 distance. So here we want velocity everyone at this position. So this thing we want. So how we can do this question everyone? Let's suppose at any t time this particle is present at x distance from the wire. So it is present at x distance from the wire. So this distance is how much? It is x everyone. So this distance is x. All right. And now the next thing is what here? This is initial everyone. Initial position velocity of the particle is 0. and this is the final position. So this charged particle is present at any t time at this x position. All right. So when this charged particle is present at x position at that time, what is the electrostatic force on this charged particle? So Fx can be written as QEx, where Ex is what? It is the electric field due to this infinite wire at this position. All right. So what is the value of Ex here, everyone? Due to the infinite wire, electric field can be written as 2k lambda by r. This is the formula. So 2k lambda, and this wire is present at x distance, so we will write 2k lambda by x. This is the electric field. And if I will write force on this charged particle at this position, so force can be written as from the Newton's second law, mass into acceleration, max. So now we have 2q k lambda by x. This thing we have. What we want a velocity. All right, this mass we will put on this side, and acceleration can be written as v dv by dx. This thing also we knows. So v dv by dx 2q k lambda by mx. All right. Now the next thing is what here? Now the next thing is what, everyone? We need to integrate here. All right. So we need to do it here, integration. So v dv we will write on this side, and 2q lambda, m is constant, and 1 by x dx, like this we can write. All right. This 2q lambda by m is constant, so we are separating this, and 1 by x is variable here. X is variable. So now we need to integrate here on both sides. So this all things are constant, that's why we are putting outside the integration. All right. Now we will put here limit of integration. So initial velocity of this particle is what? It is the 0. So u equal to 0, and here v equal to v. And here we are doing integration with respect to x. So limit of integration is what? Limit of this x is what, everyone? Initially it is present at r1 distance, and finally at r2. So r2 position we want a velocity. So this is the limit of integration. Now we will integrate this. So I'm taking new page. Right. So now do it integration, everyone. Integration of vdv is what? It is v square by 2. Put limit of the integration 0 to v, and here this 2k q lambda by m is constant. Inside the integration we have 1 by x. Integration of 1 by x is what? It is a log x, r1 to r2. All right. So this thing is happening now. After doing the integration, we are getting v square by 2. If we will put the limits, then we will get v square by 2 only. Here 2qk lambda by m is constant, and now we will put limit of the integration r2 and r1. So first of all, we will put upper limit minus lower limit, and this thing can be written as like this also, log r2 by r1. Here we are using one log property. So what is the log property? If correct, we have log a minus log b, so it can be written as log a by b. All right. So finally we have v equal to 4, and square we have, that's why we can put here under root sign. So 4 q k lambda by m log r2 by r1 with under root. So this is the final answer, everyone. This is the final answer. So I hope this thing is clear to everyone how we can do it this question. So at this R2 position, the velocity of the particle is what? It is this, everyone. Under root 4q k lambda by m log R2 by R1. Let's see next question, everyone. Calculate the electric field due to the uniformly charged rod of length L at a point P at a distance R from one end of the rod as shown in the figure. Assume the total charge on the rod to be Q. So here total charge present on the rod is what? It is Q, everyone, and the length of the rod is L here, correct? At the P point we want electric field. So how we can do it this question? First of all, I am considering here one small element on this rod, and let's suppose length of this element is dx. So length of this element is dx, everyone, and charge present on this small element is dq, correct? And distance between this element and this P point is what? It is x. So this distance is x, everyone. All right, so this is x, and this distance is r. Already this thing is given in the question. So what I will do it here, first of all, I will write electric field due to this small element at this P point. This thing we will do it. So if I will write electric field due to this small element and at this P point, so it can be written as k dq by x square. All right, this thing we will write. Now we want due to the full rod, so we have to integrate here. So we are integrating on both sides, and we need to put here limit also. When we are doing integration, everyone, we have one issue. Here we have two variables, dq and x square. So we have two variables. So now the integration is not possible. We should have one variable, correct? So we need some relation between dq and x. All right. So how we will find this relation, everyone? See it. This rod is uniform, everyone. Charge is distributed uniformly. So total charge is how much? It is Q, and the length of the rod is what? It is the L. So here we are using unitary method, correct? Unitary method we are using. So total charge on the rod is Q and the length is L. On the small element, charge is dq and the length is what? It is dx, everyone. So from here dq value we will get q dx by L. This thing we will get q dx by L. All right, so now this value we will put here, and what we will get? And the value of dq is what? It is q dx by L. This thing we will get. So integration of d is what? It is e, everyone. And now k by L. Put outside the integration. And put limit also. So first element is present here and last element is here. So limit of integration is what? R to R plus L. This is the limit of integration. All right. Now this thing can be written as 1 by x square x power minus 2 also. Correct. So now the next thing is what, everyone? We know that x power n integration formula is what? It is x n plus 1 by n plus 1 plus a. Correct. This is the formula. So this formula we will use here. So we have x power minus 2. So minus 2 plus 1 we can write here. All right, after the integration. So let's see what we will get here. Kq by L. And after doing the integration, we have x power minus 2 plus 1. So minus 2 plus 1 divided by minus 2 plus 1, and limit of integration is r to r plus l. Correct? So this thing we are getting. Now what we have to do it here, we will put limit of integration. So I'm taking next page. So now put limit of integration. So E equal to K Q by L, and this is minus 2 plus 1. So what I'm doing here, minus I'm putting outside the integration. Means I'm taking outside the bracket. So now we have E equal to minus KQ by L. And this is x power minus 2 plus 1. So this is x power minus 1. And x power minus 1 can be written as 1 by x also. Correct, everyone? And now put limit of integration. So E equal to minus KQ by L. Upper limit is r plus L. Correct. So 1 by r plus L minus 1 by r. This thing we will get. Now put negative side inside the bracket. So finally we have and this is the final answer, everyone. KQ by L 1 by r minus 1 by r plus L. This is the final answer. So electric field due to the rod on the axis of the rod is what it is this. K Q by L 1 by r minus 1 by r plus L. So I hope this thing is clear to everyone. Let's see next topic, everyone. Electric field due to the disk. So now we want electric field due to the disk. So let's suppose charge density on this disk is sigma. All right, and this is center of the disk, and at this P point we want electric field at this P point. And distance between the center and the P point is, let's suppose, x, everyone. The distance is x. Correct? And radius of the disk is capital R. And we want electric field at the P point due to this disk. So what I can do it here, we will assume one ring on this disk. So we are assuming here one ring, everyone, on this disk. All right, so this is the ring, everyone. And first of all, we will write electric field at this P point due to this ring. And let's suppose radius of the ring is small r. So radius of the ring is small r, and the thickness of the ring is dr, everyone. Thickness of the ring is what? It is dr. All right. So due to this ring, if I will write electric field at the P point, so it can be written as what, everyone? Formula already we know that due to the ring. So it is dE equal to K, and let's suppose charge present on this ring is dq. So we are assuming it is dq. Correct? So K dq x by r square plus x square power 3 by 2. And right now the radius of the ring is a small r, not a capital R. So that's why we will write here a small r. So this is the electric field due to this small ring at the P point. Now we want due to this full disk. So we need to integrate on both sides. So we are integrating dE equal to K dqx by r square plus x square 3 by 2. And what is the limit of integration? 0 to r. Alright, this is the limit of integration. Okay, now the next thing is what we need to put dq value. So charge present on the ring can be written as what? dq equal to charge density into area of the ring. So charge density into area of the ring, and it is 2 pi r dr, everyone. So 2 pi r is the circumference. If I will multiply with the thickness of the ring, then I will get area, and if I will multiply with the surface charge density, then we will get charge present on the ring. So it is sigma 2 pi r dr. This value we will put here. Integration of d is e, 0 to r k, and the value of dq is what? Sigma 2 pi r dr x divided by r square plus x square 3 by 2. All right, this thing we have. Now the next thing is what, everyone? Constant we will put outside the integration according to the rule. So we will put all constant outside the integration. So k sigma 2 pi and x and r square and x, this all are constant, everyone. So I'm putting outside the integration k sigma 2 pi x, and now inside the integration we have 0 to r dr divided by r square plus x square power 3 by 2. This thing we have. All right, this is the electric field. Copy this value. Okay, let's see next slide, everyone. So now directly we can't do it integration here, correct? So we have to take here one order. We are assuming r square plus x square equal to u. This order we are taking. And if I will differentiate this equation with respect to r, then what I will get? 2r integration of x square is 0 because it is constant, and integration of u is du by dr. All right, so from here du value we will get 2r dr. This value we will get. All right, so now from here r dr value is what, everyone? It is du by 2. All right, so this value we will put in this equation. Okay, so let's see it. Next thing, everyone. E equal to, we have k sigma 2 pi x. R dr value is what? It is du by 2. Okay, and r square plus x square is what? It is u. So it is u power 3 by 2. This thing we have. And now this integration is looking very easy, everyone. It is looking very easy, correct? We have to do it one more thing, everyone. We are doing now integration with respect to u. So limits also should be present in the form of u. So with the help of this equation, we will find relation between u and r, everyone. Okay, so minimum possible value of a small r is what? It is a 0. So if r equal to 0, then what is the value of u from this equation? If I will put r equal to 0 in this equation, then we are getting u equal to x square, correct? And if I will put r equal to capital R, then u equal to, we will get r square plus x square. All right, this thing we will get. And this is the lower limit of u, and this is upper limit. So now we have lower as well as upper limit. All right, so we will put this limit here, x square to x square plus r square. All right, so now the next thing is what, everyone? 2 will get cancelled out here. So E equal to k sigma pi x with integration here u power 3 by 2. So it is u power minus 3 by 2. So after doing the integration, we will get u minus 3 by 2 plus 1 divided by minus 3 by 2 plus 1, and the limit of integration is what? It is x square plus r square. Correct, everyone? Now the next thing is what here? This u power minus 3 by 2 plus 1. Okay, so this is minus 1 by 2. So let's see next step, everyone. K sigma pi x, and here we have u power minus 1 by 2, and in the denominator we have minus 1 by 2. Now we need to put this limit. So take next slide, everyone. Okay, so now we are putting limit of integration. Then what we will get? E equal to K sigma pi x, and this is minus 1 by 2, so it can be written like this also, minus 2 K sigma pi x, and put the limit here, everyone. So u power minus 1 by 2 can be written as 1 by root u. So it is 1 by root x square plus r square. All right. Minus lower limit. Lower limit is x square, everyone. So x square minus 1 by 2 is what it is. If I will replace u with the x square, so we have x square minus 1 by 2. So it is x power minus 1. So it can be written as 1 by x. So finally we will get 1 by x, everyone. Now multiply this x inside this bracket. So then let's read what we will get. E equal to multiply x and minus sign also. So we will get 2k sigma pi 1 minus x by under root r square plus x square. Finally we are getting this, everyone. All right. And k value we knows it is 1 upon 4 pi epsilon. Put this value also. So 2 sigma pi divided by 4 pi epsilon naught, 1 minus x by r square plus x square. Now pi will get cancelled out. Then finally we have E equal to sigma by 2 epsilon naught, 1 minus x by r square plus x square. This thing we have, everyone, finally. All right. So finally we are getting this result, everyone. You need to remember this. E equal to sigma by 2 epsilon naught, 1 minus x by r square plus x square. This is the electric field due to the disk. We need to keep this formula in our mind. Note down, everyone. Let's see this cases, everyone. So what is the case number 1 here? The point is close to the disk. So see it, electric field due to the disk formula, already we know that E equal to sigma by 2 epsilon naught, 1 minus x by under root r square plus x square. So this formula we knows, everyone. This is the electric field on the axis of the disk. So in the first case, what is the condition? The point is close to the disk, means this is a disk, everyone, and point is very close to the disk. So it is close, then what will happen, everyone? Let's suppose this distance is x here. So here is x is very small as compared to the radius of the disk. So x is very small as compared to the radius of the disk, and we can see it here. We have formula x by under root r square plus x square. So x is very small, r is very large. then what will happen? If we will divide any small quantity with very large quantity, then definitely we will get approx 0. So x by under root r square plus x square will become a 0, everyone. It is approx 0. Then electric field near to the disk, we will get E equal to sigma by 2 epsilon naught. So if point is present near to the disk, then electric field is what, everyone? It is sigma by 2 epsilon naught. All right, this is the case number 1. In the second case, what is happening? The disk is very large. Now disk is very large means radius is very large, everyone. So if radius is very large, then definitely x is very small. So again, what will happen here? R is very large as compared to x. So x is small, R is big. So ratio of x by under root r square plus x square is what? Again, it is approx 0. So in the second case, again, we will get E equal to sigma by 2 epsilon naught. Correct? So in the first case, the point is close to the disk, then electric field is sigma by 2 epsilon naught. In the second case, the disk is very large, then again electric field formula is sigma by 2 epsilon naught. And in the third case, we have infinite large seed. So when we have infinite large seed, means we have very large seed, then again electric field we have E equal to sigma by 2 epsilon naught. So remember this all three cases, everyone. For this all three cases, electric field is sigma by 2 epsilon naught. So I hope this thing is clear to everyone. Correct? Let's see next topic, everyone. Properties of electric field lines. So what is the first property of electric field lines? Electric field lines always originate from positive charge and terminate at negative charge or at infinity. So if I will take one positive charge, so from the positive charge, electric field line can generate in radially outward direction. So we have one positive point charge. So this is electric field lines, everyone. And this electric field lines going till infinite, till infinity. And we can see it here. Due to this positive charge, electric field lines are coming radially outwards, correct? Now if we will look the negative charge, everyone. So electric field lines for the negative charge radially inward. And from where it is generating? It is generating from the infinite. This thing we are assuming. All right, and terminating at the negative charge. So electric field lines always originate from the positive charge and terminate at negative charge or at an infinity. So electric field lines can generate from the infinity also. All right. And why it is happening, everyone? Why we are assuming this electric field line is going till infinite and it is terminating there. Okay, in the negative charge, it is generating from the infinite and terminating at the negative charge. Because in the universe, net charge is 0. If you will see net charge of the universe, everyone, net charge of universe. So net charge of universe is what? It is 0. So number of positive charge and the negative charge in this universe is same. All right. So that's why we are assuming here the field lines are generating from the positive charge and it is terminating at the negative charge, because negative charge is present at an infinite. That's why it is going till infinite and terminating there. Same thing is happening here. It is generating from the infinite and terminating at the negative charge because the net charge of the universe is 0. So this is the properties number first, everyone. Let's see next property, everyone. Tangent at any point on an electric field lines indicate direction of net electric field at that point. So it is representing direction of the net electric field at that point. So let's see it, everyone. We have here one electric field lines. This is electric field lines. And if I will draw tangent at this point, so this is the tangent at this point, everyone. So this tangent is representing net electric field direction at that point. So this tangent is representing net electric field direction at that point. So this is the sense of the second property. Let's see third property, everyone. An electric field lines always representing the net electric field. So electric field lines always representing net electric field. So see it, what is the sense of this point? Let's suppose we have two positive charge and we want to draw electric field diagram for this two positive charge. So how we can draw it? So we have two positive charge and we want to draw here electric field diagram for this two positive charge. So we want to draw here electric field lines, but we don't know from where to where this electric field will go. So what I will do it, I want to see it direction of net electric field at that point. So what I will do it here, I will put one test charge here. So if I will put here one test charge Q0, and we know that test charge is always positive. Alright, so we are putting here one test charge. So we will see it here in which direction force is acting on this test charge. Here between positive and positive we have repulsive force. So force is acting on test charge in this direction. Correct. And now due to this positive charge, electric force on this test charge in this direction. So this is the direction of electrostatic force. Now if I will resolve this electrostatic force in this direction and this direction, okay, same thing we will do it for this electric force also. We will resolve here and here. So this and this will get cancelled out. So you can see it here at this point, electric field, net electric field is present in the upward direction because net electrostatic force is acting in the upward direction. So force is acting in upward direction. So in same direction we have electric field also. Alright, so at this point electric field lines is going in upward direction. Now we will see it what will happen at the center of this two positive charge. So again we will put here one test charge. Alright, so see it, due to this positive charge on this test charge we have repulsive force, and due to this positive charge again we have repulsive force. So this and this will get cancelled out. Correct. So net electric field at the center is what? It is 0 because net force is 0 here. If I will draw here, so again I will put one test charge and same thing will happen here. This component will get cancelled out and we have net electric field in downward direction. Now we want to see it direction of electric field at this point. So again what we will do it, we will put here one test charge and see it. So here what is happening, we have repulsive force between this test charge and this positive, and due to this positive and this test charge we have again repulsive force. Alright, now what we will do it here, everyone, we will resolve this. So one component we have in this direction and one component we have here. One component we have upward direction and one component we have in this direction. Alright, so this and this will get cancelled out, everyone. So at this point we have electric field in this direction. Same thing will happen here also when we will put net electric field we have in this direction. So when we will put the test charge, so we will see it first of all where we have net electrostatic force. In the same direction we have electric field also. So we will get some idea, correct, what type of diagram we will get. So now let's see it. Now we have some idea. So see it what type of field diagram we will get here. It's positive charge, and this is positive charge, everyone. All right, and we can see it here. Field line is not passing from the center, and at this point it is going in upward direction. So we will get this type of field diagram. All right. And here we have electric field lines in this direction at this point. So if we want to draw the accurate field diagram, so it is very difficult. So we are drawing here approx diagram, and this approx diagram will look like this. So if you will plot field diagram for this positive charge, for this two isolated positive charge, so this type of field diagram we will get. All right. So I hope this thing is clear how we can draw the field diagram. Now let's see next example, everyone. Now we want to draw the field diagram for two positive and negative charge. So now we have positive charge and we have negative charge, and the magnitude of charge is same. Correct? Magnitude of charge is same. It is plus q, and this is minus q. So magnitude of charge is same. So see it. We want to see it electric field lines direction at this point. So I will put here again test charge. So see it. Now due to this positive charge, we have repulsive force on this test charge. Test charge is always positive. Remember this thing. Now due to this negative charge, we have attraction force on the test charge. All right. So it is attracting. Right. So it is attracting. Okay. So now electric field due to this plus q we have in this direction, and due to this we have here. Now we will resolve. So we have two components here and here. Vertical component is cancelling here. We have net electric field at this point in the horizontal direction. Correct? Because if I am putting test charge at this point, so between positive charge and test charge we have repulsive force in this direction. In the same direction we have electric field, and due to negative and test charge we have attraction force. So electric field we have downward direction, and if I will resolve, so vertical component is cancelling here, and we have net electric field in horizontal direction. Now we want to see it at the center. Net electric field is 0 or not, because when we have positive and positive charge, then net electric field at the center is 0. But now we have positive and negative charge, and magnitude of charge is same here. So electric field is 0 or not, this thing we want to see it. So when I will put here test charge, so on this test charge, due to this positive charge we have repulsive force, and due to this negative charge we have attraction force. Correct? So we can see it here, net force is acting in this direction. So in this same direction we have electric field also. So at the center of the charges, electric field is not 0 here. All right. So now we have some idea. Correct? At the top, at this point electric field line is going in this direction. At the center electric field is going in this direction. So if I will draw the field diagram for this positive and negative charge, and it is isolated, everyone, means in the system only we have these two charges. So this type of field diagram we will get. All right. So this type of diagram we are getting here, everyone. So this is the field diagram for this positive and negative charge. So I hope this thing is clear to everyone. Let's see next property, everyone. Property is number 4. two electric field lines never intersect because at their intersection point they would suggest two possible directions for the net electric field, which is impossible. So let's suppose we have two electric field lines and these two field lines are intersecting. So what will happen at the intersection point? This is the intersection point. So for this field line, this is the direction of net electric field. All right, and let's suppose this is E1, and for the second line, net electric field in downward direction. So here we have two directions of this net electric field, which is impossible, everyone. That's why two electric field lines is never intersecting. Let's see next point, everyone. The intensity of electric field at a point is directly proportional to the density of electric field lines in that region. The intensity of electric field at that point is directly proportional to the density of electric field lines at that region. So what is the sense of this point? So let's suppose this is the electric field lines, everyone. So let's suppose this is the electric field lines. This is a non-uniform electric field. So here we are choosing 2 points, P1 and P2, and we want to see it intensity of electric field at this P1 and P2. So how we can decide where we have greater intensity and where we have less intensity? We will see it density of electric field lines. So here if I will consider A area here and here, so here I am considering A area, same thing I am doing here also, A area. So we can see it here from this A area, how many field lines are passing? Here 3 lines are passing and here only 1 line is passing. Here field lines are closer and here it is present at far distance, correct? So density of field lines at the P1 point is greater. That's why intensity of electric field at the P1 point is greater, everyone. That's why E1 is greater than to E2. So density of field lines is representing intensity of the electric field, everyone. If density of field lines is greater, then intensity at that point is greater, everyone. So remember this point, correct? Let's see next property, everyone. Property is number 6. Electric field lines never form a closed loop since they cannot originate and terminate at the same charge. So what is the sense of this property is number 6? Let's see it, everyone. Let's suppose we have positive charge. So field line is generating from the positive charge and terminate at the positive charge. This thing is not possible. So that's why it is not making closed loop. So this is the property number 6. This is not possible. Field lines are not making closed loop. Let's see it. Property is number 7, everyone. The number of electric field lines is directly proportional to the charge magnitude. So this is the property number 7. And what is the sense of this property number 7? Let's see it, everyone. Let's suppose we have 1 coulomb charge and we have 2 coulomb charge. Alright, we have 1 coulomb charge and we have 2 coulomb charge, and we want to draw field diagram for 1 coulomb and 2 coulomb charge. So we have here 1 coulomb charge and we want to draw field diagram for this 1 coulomb charge and for this 2 coulomb charge. Alright, so number of electric field lines is directly proportional to magnitude of charge. So if we are representing 1 coulomb charge with 4 line, so for 2 coulomb, how many number of field lines we need to take? Think it, everyone. If for the 1 coulomb charge we are representing with 4 line, then for 2 coulomb charge we need to take 8 line, correct? Because here we have proportionality between the magnitude of charge and number of field lines. That's why it is happening. If we are representing 1 coulomb charge with 4 line, and for the 8 coulomb, for the 2 coulomb we are taking 10 line, then it is wrong everyone. All right. So if we are representing 1 coulomb charge with the 4 line, then for the 2 coulomb it should be 8 line. And if suppose we have 3 coulomb charge, then for this how many number of field lines we need to take? So it should be 12 line, because we have proportionality. All right, that's why. So for the 1 coulomb we have required 4 line. So this is the field diagram for 1 coulomb charge, and if I will draw for the 2 coulomb charge, then we need to make here 8 lines. So here we need to draw 8 line everyone. And for the 3 coulomb charge we have required 12 line. All right. So this is the sense of property number 7. Let's see one example everyone. So we want to draw the field diagram, correct? So let's suppose we have 2 coulomb charge and -1 coulomb charge, and for this we want to draw the field diagram. All right. So what type of field diagram we will get? Let's see it everyone. And this both charges are isolated, correct? So only in the system we have this 2 charge only. So inside the system only these 2 charges are present. Now the next thing is what? Here I am taking one reference. 1 coulomb charge I am representing with 4 line, correct? So how many line we will take for 2 coulomb charge? This thing already we know that it is 8 line. So for 1 coulomb charge I am taking 4 line. So for the 2 coulomb charge we will take 8 line. All right. Now the next thing is what? -1 coulomb charge is negative and +2 coulomb charge is positive. So 2 coulomb charge will generate electric field lines, and -1 coulomb charge terminate this electric field lines. This thing will happen. So how many number of lines this 2 coulomb charge will generate? It is total 8 everyone, correct? See it, what type of diagram we are getting here. So this type of diagram we will get, and this arrow will go outside because this is positive charge. Now it is correct. So we can see it here, 2 coulomb charge is generating field lines, it is 4, and -1 coulomb charge is terminating 4 lines, correct? So this thing is happening here. Let's see next example everyone. So in this example, what is happening everyone? Example number 2. Here we have +2 coulomb charge, here we have -1 coulomb charge, and here we have -1 coulomb charge. And for this we want to draw field diagram, electric field diagram we want to draw, correct? So first of all we will take a reference. For 1 coulomb charge we are taking 4 line. So for the 2 coulomb charge it should be 8. This is positive charge, so positive charge is generating field lines and negative charge terminate field lines, correct? So +2 coulomb charge generate total 8 line, 8 line everyone, correct? So 8 line we want to draw here. Here we need space everyone, so -1 coulomb charge I am taking here. So let's see next 4 lines. So this is rough diagram everyone, it is not accurate. Approximately it is correct, but this type of diagram we will get, correct? So I hope this thing is clear how we can draw the field diagram, correct? And now let's see one more example everyone. And this example I am giving to you in a homework, do it from yourself. So we have -2 coulomb charge, +2 coulomb charge, and -1 coulomb charge. For this we want to draw the field diagram. So this is your homework question everyone, do it from yourself. -2 coulomb, +2 coulomb, and -1 coulomb charge. Alright, for this we want to draw the field diagram. Let's see next property everyone, property number 8. In a uniform electric field, the electric field lines are straight, parallel and equally spaced. So if we want to represent uniform electric field, so like this we can represent. Here we are making a straight line and separation between this all the lines are equal here, correct? And if you want to make non-uniform electric field everyone, then you can see that space is not equal, correct? Space is varying here. And field lines are not straight also. So non-uniform electric field we can represent like this, and for the uniform electric field lines we will make straight and parallel lines. So I hope this thing is clear how we can represent uniform electric field and non-uniform electric field. Let's see this question everyone. If number of electric line of forces emerging from the charge plus 4q are 28, then the number of electric line of force emerging from charge plus q are, correct? This is the question. So we know that between the field lines and the magnitude charge we have proportionality, correct? So here we have proportionality between the field lines and the magnitude of charge. So we will use here unitary method everyone. Unitary method can be used here because here we have proportionality between the magnitude of charge and the field lines. All right, so let's see how we can do it this question with the help of unitary method. So for the 4q charge, how many number of lines we are using? It is 28. So for the q charge, let's suppose number of field lines required is n. So value of n is what? It is 28q divided by 4q. So how much we will get everyone? N equal to we are getting 7. So number of field lines required to represent plus q charge is 7. So the correct answer for the question is options A everyone, 7. Let's see next question everyone. Two parallel infinite line charges with linear charge density plus lambda coulomb per meter and minus lambda coulomb per meter are placed at resistance 2R. So distance between this infinite wire is how much everyone? It is 2R. You can see in this picture. What is the electric field midway between the two line charges? So let's suppose here we have one point B and it is present in between this wire. And at this point we want net electric field. This is the question everyone. So we can do it here everyone. First of all we will put here test charge. So from the test charge we will get direction of electric field at this P point. So we can see it here on the first wire we have positive charge. So between positive charge and this test charge we have repulsive force, correct, E1 in this direction. And on the second wire we have negative charge density. So between this second wire and this test charge we have attraction. So we can see it here E1 and E2 both are in the same direction. So here net electric field we have in this direction everyone toward the right, and E1 and E2 both are adding here. All right, so net electric field at the P point is what? It is E1 plus E2. Now we know one thing everyone, due to the infinite wire, electric field at r distance or at a d distance can be written as what everyone? Do you know the formula? Yes, we know this formula. It is what? It is 2k lambda by r. Due to the infinite wire, electric field at r distance is what? It is 2k lambda by r. Complete formula is what? K lambda by r sine theta 1 plus sine theta 2. Theta 1 and theta 2 for the infinite wire is 90 degree. Correct? Sine 90 value is 1. That's why after simplification we are getting 2k lambda by r. So due to the infinite wire, magnitude of electric field is what? It is 2k lambda by r. So even value 2k lambda by r. R is distance between the point and the wire, and the second wire again is 2k lambda by r. So 2k lambda by r plus 2k lambda by r. So it is 4k lambda by r. Now we will put here k value, which is 1 upon 4 pi epsilon naught. So 1 upon 4 pi epsilon naught 4 lambda by r. Now 4 will get cancelled out. So we will get lambda by pi epsilon naught r. This is net electric field at the P point. So net electric field at the P point we are getting lambda by pi epsilon naught r. And now if we will check options, then we are getting option number C. So C is the correct answer for this question. So I hope this thing is clear to everyone how we can do it. Let's see next question everyone. A particle of charge -2 coulomb and mass 0.1 gram moves in a circle of radius 10 meter around an infinite long line charge of linear charge density +2 coulomb per meter. The time period of the motion is what? So we want time period of the motion everyone. So in this question what is happening here? We have infinite long wire, you can see it here. All right, infinite wire we have, you can see it here in this picture, and around this wire we have one charge particle, and the mass of this charge particle is 0.1 gram, correct? And it is moving in the circle. So time period we want here. All right, so this question I'm giving to you in a homework everyone, do it from yourself. All right, so when it is moving in the circle around this wire, then we have centrifugal force, correct? And we have electrostatic force also, because between this wire and this negative q charge we have attraction force, and centrifugal force is acting in radially outward action, correct? So this is the hint for you for this question everyone. So use this hint and solve this question. So this is our homework question everyone, do it from yourself.